For much of the book, we focused on triangles because they're so important to what we build as people. Um, but now we're going to focus a little bit about circles. And if you look at our universe, not the triangle, but the circle is the dominant shape that you'll see from the largest of objects like galaxies to large bodies like planets or like Earth, and to the smallest shapes like atoms. You can see the circular shape that they all take because of the force of gravity. So the circle is definitely the predominant shape of our universe, and so that makes it very important. Um, so what is a circle? A circle is simply the set of all points in a plane that are equidistant, the same distance from a given point, and usually we mean the center. So if you look at a bicycle wheel, it's a perfect example. That spoke is 13 inches, so this point right here is 13 inches away from the center point. And if I take all of the points that are 13 inches away, another one there, and another one there, and if I keep going around, right, what you would end up with, you could do way more than just the spokes. You would end up with all these points because all these points are 13 inches away from the center, and so that's how you get a circle. It's all the points equidistant from a center. Now, naming a circle, generally name it just with the center. So if this is center P, then we could call this circle P, or you see the little diagram there, a little circle with a dot in the middle meaning the center, circle P. So there are some important segments with circles. Some of them are contained within a circle. So again, if we have a center, and these two that we start with, you guys are going to be very familiar with. If we go from the center to a point on the circle, that is a radius. And that could go anywhere on the circle, but it's going from the center to a point on the circle. And just going to switch colors here. Now, if I went all the way across, I went through the center, and basically I have two radii, that would be a diameter. So again, a diameter goes from one point on a circle to another through the center. If it doesn't go through the center, it is not a diameter. And if it doesn't go through the center, like this, so this is going from one point to another point on the circle, but it's not going through the center, and that is called a chord. So a chord goes from one point to another, but it does not go through the center. Now, there are two important segments that we need to discuss that cross through circles, or touch the circle, but are not contained within it. And the first one would be just a line, like imagine a line that just went right through, it's going through 2 points on the circle, and that's called the secant line. So the secant line in this case is very much like the chord in the first one, except that it continues, it extends, it doesn't stop. It doesn't stop at the edges of the circle. Okay, and then there's one more, and this is the one we're going to focus the most on, and this is called a tangent. So the secant line touches the circle in two places. A tangent only grazes the circle in one point. So if we take this line, and it goes and it just nicks the circle there, that is called a tangent line. And you can think that's where we get the expression goes off on a tangent, right? Because if you go off on a tangent, you're not quite touching on the point, you're not quite hitting the circle, but you're somewhere in the neighborhood, right? You're not going off on you're not talking about something totally unrelated. You're kind of right on the edge of what's important, and that's the tangent line. It's right on the edge, it touches the circle at one point. And a lot of what we're going to discuss following focuses on tangents. So speaking of tangents, circles can have common tangents, which means a line that is tangent to more than one circle. And the number of those common tangents is going to depend on how the circles intersect. So we'll start on the left with 2 points of intersection. You can see these circles intersect there and there. And now a tangent line, remember, it's just going to graze each circle at one point. So you can imagine that if you had a line lined up just like that, it would graze each of those circles. So it's a common tangent. And you can probably already see the other option would be on this side. And you could draw a line that just grazed through those. So you could draw two common tangents there. Now moving on to 1 point of intersection. This is a little interesting because you can see right away, just like the last example, we could have this common tangent line and we could have this common tangent line. But remember, in this example, we're saying 1 point of intersection. So we're saying that they're only touching at 1 point here. So we could actually draw a third common tangent that would go through that point, right there, because that's only touching at that one point, even though it looks a little, close in there. There's one point of intersection. Again, here we have one point of intersection, and since the one circle is in the other circle, it's sort of protected by that. We can only draw the one tangent line, because if we tried to draw any other line tangent to the inner circle, it would be cutting through the outer circle, and it would not be a tangent. All right, so now 0 points of intersection. Right away, you can see, just like the other examples, I can do that, 1, and that, 2. Now, if we look at this example here in the middle, so we can see, we could cut through. I could do maybe it'd be right there and there. I could cut through, just graze that one and just graze that one. But you're probably already thinking, well, if you can go in that direction, then you could also go in that direction. And so if you have 0 points of intersection, you'll be able to find 4 common tangents. However, if you have 0 points of intersection, because like on this example, the inner circle is inside the other one, there's no common tangents, because if you did something tangent, let's say you did this, and it was tangent to the inner circle, you're cutting through the outer circle. And if you did something tangent to the outer circle, well, you're never grazing the inner circle. So there are 0 common tangents in this case. All right, some other characteristics of tangents. Number 1, a radius drawn to the point of tangency. So here's your point of tangency, right? And here's your radius. Is always going to be perpendicular to that tangent line. So right there, that is perpendicular to the tangent. Because imagine if you drew some other radius, let's say this, that wasn't perpendicular to the tangent. Well, it's not a radius anymore. It's not touching at the edge of the circle, right? So the only way they're going to meet is if that radius is perpendicular to it. Number 2, 2 tangents to a circle from the same point are congruent. So we have point C here. We have tangent CA, and we have tangent CB, and the only way they can be tangent to the circle from the same point C is if they are congruent. Okay, so those are 2 key characteristics. 1, radius drawn to the point of tangency is perpendicular to the tangent, and 2 tangents from the same point, in this case C, have to be congruent. Otherwise, they couldn't both be tangent to the circle. And so, using these characteristics, we can solve some problems, right? So, question 1, verify that this is a tangent to the circle. So they're giving you that PT is a radius, so you know this is a radius, right? And you know that, and what they're asking is ST, right here, is ST, from here to here, a tangent to P? Well, what we know is, if it's a tangent, right, if it's a tangent, then this is perpendicular. And if that's perpendicular, it's a right triangle. And if it's a right triangle, then a squared plus b squared will equal c squared. So that's how we're going to test. So let's see. So the hypotenuse would be 37. So what we're going to check is 12 squared plus 35 squared equal to 37 squared? And remember, I'm going to put a question mark there because that's what we want to find out. So 12 squared is 144. I'm going to check out 35 squared on the calculator. 35 squared is 1,225. And 37 squared is 1,369. And if we add these together, indeed, we get 1,369. And so we know that it's a right triangle. And if it's a right triangle, we know that angle STP is a right angle. And if that's a right angle, we know that the radius, TP, is perpendicular to TS. And if the radius is perpendicular to that line, then it is indeed a tangent. So yes, it is a tangent. It is a tangent. Okay. So here's a similar problem. It's a little bit more challenging. They ask us to find the radius of the circle. So they're asking us, what is this length right there? And so remember, there's two things we know about tangents. One is that they're perpendicular to a radius of the circle. And the other one is that two tangents from the same point of the circle are congruent. But in this case, we only have one tangent, AB. So that's not going to apply. So it must have something to do with the fact that the radius is perpendicular. So it says it's a radius, so we know this is perpendicular. And if that's perpendicular, we know that that's a right triangle. And if it's a right triangle, then we know that the Pythagorean theorem will apply. We know that a squared plus b squared equals c squared. And this is where the problem gets a little more challenging, because they haven't given us exactly what all the sides are, right? But we do know one is 80, so we know that 80 squared plus r squared, the radius squared, is equal to the hypotenuse squared. And the key here is just to realize that the hypotenuse is just 50 plus r. And if we square that, we'll get the sum of the legs squared. So 80 squared is 6,400. And r squared is just r squared for now. Now 50 plus r squared. You could expand this if you want. So you could say 50 plus r times 50 plus r. And then so you would distribute. So 50 times 50 is 2,500. And then 50 times r is plus 50r. And then r plus 50 is plus 50r. And then r times r is r squared plus r squared. So you'd end up with 2,500 plus 100r plus r squared. And so you could write that in. So 2,500 plus 100r plus r squared. Now, we just need to solve for r. So you might think, oh, that's a little confusing, except I can do minus r squared on both sides, and guess what? Those are gone, and I would be left with 6,400 equals 2,500 plus 100r. So notice we only have one r left, which is pretty convenient. So now I'm going to subtract 2,500 from both sides, and when I do that, I'm going to get 3,900 equals 100r, and I'm going to divide by 100, and I'll get 39 equals r. And so what appeared to be, r is 39. And so what appeared to be a really challenging problem wasn't so bad. You just had to realize that the hypotenuse in this case was just the 50 plus r. One more example, okay? And in this, remember, we know two things about tangents. There's two characteristics. One is that it's perpendicular to a radius of circle, but in this case, there's no radius that we're looking at. The other one is that we know that two tangents from the same point are congruent. And so it says RS is a tangent to circle C and at S, and RT is a tangent to circle C at T. So we know that this RT is a tangent and RS is a tangent, and they start from the same point. So we know that this is congruent to that, and so we know that 28 is the same as 3x plus 4. And so we can subtract 4 from both sides. 24 equals 3x. We can divide by 3, and we know that x is 8.